All right, I'm going to do my lecture this way, at least for the moment. In the fourth lecture, I left off with discussion of convex sets. So, I wanted to do a little work with them. Just a quick review here of this. Let V be a vector space. Now, and let S be a subset of V. Now we say that S is convex if for any, let's say P and Q in S, we have that the segment, the line segment from P to Q is a subset of S. All right. P and Q are vectors since they're elements of S, and S is a subset of V, hence P and Q are actually elements of V. Now, you could put little arrows over these and stuff like that, but like in your textbook, I don't think I'm going to, bother. By definition, the line segment from P to Q, as we saw in chapter 1 of your text, that is the set of vectors of the form 1 minus t times p plus t times q, such that t is anything from 0 to 1. All right, so we have here S and a point P and a point Q. So there's our line segment there, right? That is our point, that is our line segment P to Q. See, it kind of mimics the interval notation that you know from algebra and calculus. It's the, but again, V is any arbitrary vector space, so we're not necessarily on the real number line here. So in your homework in section 3.3 of the book, now let's see if we can find that. 3.3 of the book. Yeah, so we have these problems here on page 104. And, well, I could do one of those, although they're all supposed to be homework. So for the time being, I think I'll do a different problem that nonetheless works with the idea of convex sets. I don't know if this is in the book here, this problem that I'm going to do. So, let's do this. Even if it's in the book. No reason why we can't do it here. I think I need another piece of paper. Okay, let's do this. An open ball in Rn with radius R and center C. Is the set, let's call this S. S equal to, well, it's the set of all vectors in Rn I think in this context, I will put the little arrow over C here. It's a center. It's a point in Rn, the center, right? And we're looking at elements of Rn such that the distance x is from C, which is that's the distance between x and C, is less than R. The closed ball is almost the same thing, except this is a less than or equal to if you want it to be a closed ball. This was discussed in your wonderful book in chapter 1. In fact, just to be clear, this is, here it is, page 19 of the book. Circle, disc, sphere, ball, all these good things were discussed there. All right, well, anyway, what we want to do is show that S is a convex set. For any center C and radius R. That's irrelevant. Okay, so what we have to do is show, so here it is, proof. All right, so what do we have to show? To show that S is convex, we need to show that for any 2 points in S, P and Q, the line segment from P to Q is a subset of S. To show that PQ is a subset of S means to show that anything that's in that line segment is an element of S. All right, well, the line segment from P to Q is, by definition, this set of objects here. So if you're in the line segment from P to Q, you're something of the form 1 minus T times P plus T times Q for some T, for some real number T between 0 and 1, inclusive. So what we do is we need to just go ahead and take 2 points, P and Q in S. Let P and Q be elements of S. These are arbitrary points in S, okay. Now we need to show what I'm writing in the red is not something you'd normally put in the proof. However, for expository purposes, I'm putting this down. What we have to do is show that PQ is a subset then of S. Which is to say, show any, let's say, what do we call it, X. For any point X in the segment P to Q is in S. Right. Well, to do that, just say let X be in the segment from P to Q. I'll put a little harpoon. I'm going to be consistent. On this page, I'm putting little arrows, or harpoons are called sometimes, over everything that's an element of R in. So let X be an element of this segment, P to Q. What does that mean? Again, if you're in that segment, you're something of this form for some T between 0 and 1. So X is equal to 1 minus T times P plus T times Q for some T element of 0 to 1. So we have to show that this X, which is in this segment P to Q, okay, and therefore has this form, we have to show that this thing is in S. What is S? S is anything in Rn whose distance from C is less than R. All right. So we just have to need to show that the distance between x and c is less than r. That's what it takes to show that x is going to be an s. All right, well, what is this looking like? The distance between x and c, x is this expression here. So that's 1 minus t times p plus t times q. Okay. Minus c. And we want to do something cute. This is not an obvious step necessarily, but here's how it goes. Okay, so let me write this again. 1 minus t p plus t times q. Minus c is going to break up into a 1 minus t times c plus a t times c. If you look at that, that's 1 minus tc plus tc. Oh, well, okay, the c has to distribute. So it's a c minus ct plus ct. Meaning that all the stuff here in this pair of brackets is just c still. This is exactly that. Just do a little arithmetic. Okay. And then what you do is you put the stuff with 1 minus t in front of it together. We have a 1 minus t p minus a 1 minus t c. So that writes down as 1 minus t times p minus c. And then we have a tq minus a tc. That is to say, we have a t times q minus c. Okay. So then, in your text, on page, I had it here and then I lost it. So on page 28, you see there that theorem 4.3, and that is called the triangle inequality, that the norm of the sum of two vectors is less than or equal to the sum of the norms of those two vectors. All right, we're using that here. We have the norm of this vector plus this vector. By the triangle inequality, this is less than or equal to the norm of 1 minus t times p minus c plus t times q minus c. So then, maybe make a remark here. By the triangle inequality. Triangle inequality is sometimes written lazily as a triangle with an unequal sign after it. Okay. And then 1 minus t and t are scalars. They can come out of the normality bars, the normals. The norm. So they're non-negative scalars, right? So 1 minus t can pop out of there, and then we have the p minus c left in the magnitude bars, you might call them. Same here with t. Remember, t is going to be between 0 and 1, so it's not negative, so it comes out cleanly. Then times the magnitude or norm of q minus c. So where we stand? We could have mentioned this at any point, but now we definitely need to have it mentioned. By having P and Q in S, what does that mean exactly? Anything in S is something whose distance from C is less than R. So we have here, because P is in S and Q is in S, that means that the norm of P minus C is less than R, and likewise the norm of Q minus C is less than R. That's in, well, by this we mean this. So coming back down to here, this is less than R and that's less than R. So this whole expression is less than 1 minus t times R plus t times R. And then we have a 1 minus tr plus tr is equal to, all right, we have an r minus tr plus tr is r. So the norm of x minus c, that is to say the distance between x and c in Rn, is in fact less than r. All right, we just found out that this guy is less than r. Now, that just means then that this segment, PQ, is in fact a subset of S, as we wanted to show. To be formal about it, we have here, so this means that X is in S, since X, as you see here, is an arbitrary element of the segment from P to Q. We have then that everything in the segment from P to Q is in fact in S. So that is to say, the segment from P to Q is a subset of S. So we have PQ is a subset of S. Now, PQ were two arbitrary points in S. So we just found out that for any 2 points in S, the line segment connecting them is also in S. So this means that S is convex. Any line segment connecting any 2 points in S is a subset of S, convex by definition. Therefore, S is convex. And I make a little rectangle here, kind of or square, just to indicate that the proof is done. Now, so there's an example of showing that, for instance, open balls in Rn are convex sets. It makes sense. If you take any 2 points in a ball, the line segment connecting them would still be in that ball. There's no way to get around that. This is actually something to be generalized for open balls in any arbitrary vector space, but when you have an arbitrary vector space, you do need to have some kind of a thing defined that you can call a norm. We know about the norm in Rn, that we know. In chapter possibly 7 in your text, we get into, no, chapter 6 in your text, we do get into defining norms on other kinds of vector spaces other than Rn. And then, you know, these kinds of, you know, proofs that we're doing here actually are applicable there too. All right, so that's one example. All right, let's do something else. All right, we're getting into section 3.4 of the text, which is on linear independence. All right, as usual, let V be a vector space. We say that the vectors v1 to vn in V, the vector space V, are linearly independent if you set a linear combination of v1 through vn equal to the zero vector, necessarily implies that all these scalars c1 through cn have to be zero. Okay, that's all there is to that idea of linear independence. The vectors v1 to vn in the vector space V are linearly independent if, when you set a linear combination of the vectors v1 through vn equal to the zero vector, that necessarily implies that all these coefficients, c1 through cn, these scalar coefficients, they're all zero. Otherwise, if this is not the case, then you say that these vectors are linearly dependent. Otherwise, we say v1 to vn are linearly dependent. I'll just say there's other terms that are used. Okay, that's a definition. So if you have a set of vectors like this, v1 to vn, you say that this set of vectors is a linearly independent set I think I'll abbreviate linearly independent as Li, just to save time from now on. But this is a linearly independent set if the vectors v1 to vn are linearly independent. Trying to write that as L dot I dot, so, all right. Okay. So, where do we go from here? Quick example. The vectors E1, which has components 1, 0, and E2, which has components 0, 1 in R2, are linearly independent. How does that, so you show that just by doing this. If you set up C1, E1 plus C2, E2, and just set that equal to the zero vector, what do you get? What's C1, E1? C1 times this vector 1, 0 is C1, 0. That's that guy. Plus C2, E2 is 0, C2. And you're setting that equal to the zero vector, which in R2 is 0, 0. And then adding these two vectors gives you C1, C2 on the left-hand side there, and on the other side you got 0, 0. And now you can see that C1 is 0 and C2 is 0. Therefore, E1 and E2 is a linearly independent set in R2. More things here. We'll look at other examples soon. But let's have another definition. A basis for any vector space V is a linearly independent set let's call it B, such that the span of B is equal to V. A basis for V is a linearly independent set of vectors that are in V. Let's call that, say, B, such that the span of the set B is V. Recall the span of a set of vectors like V1 through Vn in general is the set of all the linear combinations of the vectors V1 to Vn. So it's the set which is sum k from 1 to n ck times vk such that each ck is a real number. C1 dot 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 up to Cn, they're all elements of the reals. That is to say that the span of the set of vectors V1 through Vn is the set of all the possible linear combinations of the vectors V1 through Vn. We're assuming a vector space V that's like, say, over R. Let V be a vector space. It can be over any field F, but I'll just stick with R for now because it gets the point across. So these would be reals. If we're looking at a vector space over, say, the set of complex numbers, then these scalars, C1 through Cn, should be elements of the complex numbers, the set of complex numbers. In general, replace R with any other kind of field F, and then here, likewise, replace R with the field F. Now, what we have found in this example is that this set E1, E2 is a linearly independent set in R2, but we also know that this set spans R2. The set of vectors E1, E2 spans R2. Notationally, we might write that as span E1, E2 is equal to R2. So what does that mean again? Well, any combination of the vectors E1 and E2 is going to be in R2, so the span of E1, E2 will be a subset of R2, certainly by the closure properties that apply to any vector space, like R2. The thing that's not always true is that anything that's in R2 will be in the span of whatever set of vectors you're looking at, like E1, E2 here. So to show that the span of E1, E2 is equal to R2, it's sufficient to just show that R2 is a subset of the span of E1, E2. So how do you need only show that R2 is a subset of the span of E1, E2 to verify equality. By equality, I mean this equality right here. Yeah, so show that anything that's in R2 is representable, can be portrayed as a linear combination of E1, E2. No, that's easy. Let AB be an element of R2. We just have to show that AB is in fact in the span of E1, E2, right? Stuff we did in lecture 4. So that means to say find constants C1 and C2 such that C1 E1 plus C2 E2 is equal to AB. Okay, this way we show that the vector AB in R2 is expressible as a linear combination of the vectors E1 and E2, and hence the vector AB is in the span of E1 and E2. Now we just saw already, right, that C1 E1 plus C2 E2 is just C1 C2, right? So what we have here is C1 C2 on the left hand side, and that equals AB, and that's making clear that C1 should equal A and C2 will equal B. So we have now found C1 and C2 such that this linear combination of E1, E2 is equal to the vector AB. Merely let C1 be the A and C2 be the B. So this is in fact a basis for R2. It spans R2, and E1 and E2 are also linearly independent. We need a linearly independent set B with the span of that set B equaling the vector space V. We have that. This set of vectors E1 and E2 in R2 is in fact known as the standard basis for R2 because it's the most convenient one. It's the easiest. It's not always the one easiest to work with in all applications. We will look later on in this course at how we can identify different bases for a given vector space and change from one basis to another depending on depending on the needs of a particular problem. But we're not there yet. That'll be stuff more for the next chapter. Well, at least it's a few sections away, let's just say that much. So, okay. We call E1, E2 the standard basis for R2. More generally, E1 equal 1, 0, 0, dot, 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 0. E2 equal to 0, 1, 0, dot, 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 0. And this is an n by 1, and this is also an n by 1 matrix. Keep on going, all the way to En. 0, 0, 0, dot, 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 and all the way at the bottom there's a 1, and everything else above it is zeros. Again, an n by 1 vector. This collection of n vectors is the standard basis for Rn. So put it between braces, make this a set of vectors. This set is the standard basis. For Rn. So what E1 is depends on, you know, what Rn you're talking about. In R2, E1 is 1, 0. So simple enough. But in Rn, E1 is the n by 1 vector with a 1 at the top and all zeros below it, right? So, all right. Just taking a simple problem here, showing that you have a basis for a given vector space. It's convenient to just stick with R2 simply because the computation's less busy, but any problem like this that you might encounter in R3 or R4, it's the same kind of stuff, just more to do algebraically. Alright, so determine whether the set 1, 1, the set containing the vectors 1, 1 and negative 2, 1 is a basis for Rn. So, okay, yeah, I don't need to write anything there. So we need to show first that they're, it doesn't actually matter which of these you do first. We could show that they're linearly independent first and then show that they span R2. Sorry, this should be an R2. Okay. Okay, we can show they're linearly independent first, then show that they span R2, or vice versa, whatever you like better. I'll show a linear independence first. Suppose, why don't we call this, I don't know, U, and we'll call this, U1 and call this U2. Okay, so suppose that C1 U1 plus C2 U2 is equal to the 0 vector. We just have to show that C1 and C2 both must equal 0, and there's no other way around that. C1 times U1 is C1 C1. C2 times U2 is negative 2 C2 C1. Oops, I meant to say C2. Right. Negative 2 C2 C2. Right, we're just, this is this. And this is 0, 0. And that gives us C1 minus 2 C2. And this is C1 plus C2, and that equals 0, 0. That's a system, right? It's just a simple homogeneous system of linear equations. Yeah, you just have to solve that. I would say, you know, if we just simply subtract the bottom equation from the top equation, I think you can see then that you get C1 minus C1 is gone, negative 2 C2, take away C2 is negative 3 C2 is equal to 0 minus 0 is 0. And negative 3 C2 equals 0 is clearly implying that C2 is 0. With that and the second equation, we find, of course, that C1 is 0 also. so C1 equals C2 equals 0 necessarily obtains from this supposition. When you have that, you must have this. Therefore, these vectors u1 and u2 are linearly independent. We can say u1, u2 is a linearly independent set. Now, do they span R2? Do a time check here. All right, so now we need to show that anything that's on R2 is expressible as a linear combination of u1 and u2. Show that R2 is a subset of the span of u1, u2. I.e. show any x, y in R2 is expressible as some linear combination of the vectors u1 and u2. Any xy in R2 is such that xy equals c1 u1 plus c2 u2 for some choice of scalars c1 and c2, which will be, in other words, real numbers in this context. All right, far out. Well, let's see what we got. In fact, this is pretty much what you work with. That sets up as a system, with the unknowns being c1 and c2, not x and y. I mean, this here just becomes, well, let's put it over here, I guess. xy is equal to, I mean, we already figured out that c1 u1 plus c2 u2, which is this, right? We already figured out that that's this guy, right? So, you know, this is c1 minus 2c2, c1 plus c2. So xy has to equal that. That's a system. I guess my arrow should be here. Forget about that. So then we got c1 minus 2c2 is equal to x, and c1 plus c2 is equal to y. And that makes our system up. We again solve this for c1 and c2 in terms of x and y. Might have been better for me to use an a and b here. So we're not used to thinking of x and y as being thought of as known constants, right? And the c1 and c2 are the unknowns, but that's precisely what's going on here. But the idea is that this xy is any point in R2. It's completely arbitrary. It can be anything. Here's what we can do. Actually, pretty much the same gimmick as before. We can subtract one equation from the other or something. Right. And you get negative 3c2 is equal to x minus y. And then you find that c2 would have to be y minus x over 3. The minus sign there, the negative sign technically, turns that around there, right? That's a real number, right? If x and y are real numbers, which they are by virtue of the fact that x and y by hypothesis are in R2, then certainly this fraction is a real number. So C2 is some obtainable real number. Now we just have to figure out C1, if at all possible. And it is. From this second equation, you can see that C1 is nothing more than the y minus the C2. So we put our real number that we found for C2 there and subtract it from the y, and that gives you yet another real number, so we're good. This is y minus x over 3. Now you can just put these together, of course, and get 2y plus x over 3. That's great. So C1 is this real number and C2 is that real number. Let me just write, well, that's C1, right? So C1 is this. So we have our C1 and C2 figured out. You can test it out if you have your doubts. Substitute this expression for C1 and this expression for C2 here and here respectively, and add these guys up. You'll find you get xy. So there exist real numbers C1, C2 such that C1 U1 plus C2 U2 is equal to our random arbitrarily chosen vector xy in R2. Therefore, the set U1, U2, the set of vectors U1, U2 spans R2. Yeah, I don't know if there's anything else I should write here. I'll just say it, right? We have that the set U1, U2 spans R2. It's also a linearly independent set. Therefore, by definition, it's a basis for R2. All right. Okay. Here's another problem. We've already seen that the solution set to a homogeneous system such as this is a vector space in its own right. Here we have a system involving x, y, z. So solutions to this system will be ordered triples x, y, z, and hence would be points in R3. And the solution set to this system, in fact, will consist of a set of points in R3 that constitutes a subspace of R3. We want to find a basis for that subspace. A subspace of any vector space is a vector space in its own right, so it would stand to reason that it might yet have a basis. And in fact, the real key here is just to solve the system, really. So, let's see. From this first equation, we have that x is y minus 2z. We get that from, well, why don't we call this 1 here, and we'll call this 2. So from 1, we have this. Put this into 2. Two times the x, well, that's now 2 times y minus 2z plus y plus 3z equals the 0. Alright, now solve this for one of these variables. We have to sort this out a little. We got 3y minus z is equal to 0, right? So it looks like this one's easily solved for z. Z is 3y. Now you put that back into here. From this, we have that x then is y minus 2 times z, which is 3y, is negative 5y. So we have solution set to this system here, call it S, say, is the set of points x, y, z such that x is negative 5y and z is 3y, y itself any real number. Then we can make this nicer. X is negative 5y. Why don't we just go ahead and put that in there for x, and y stars as itself, and then z is the 3y. And again, y is any real number. And if you look at this, then you actually can factor the y out of this, right? And in fact, why don't we just call the y's t's, because well, it's done. So we have t times negative 5, 1, 3. T is any real number. This is otherwise known as the span of the set containing the single vector negative 5, 1, 3. Now then, I mean, it's all linear combinations of this vector. That's what the span is, right? And all linear combinations of this vector, negative 5, 1, 3, are just, in this case, well, all scalar multiples of that vector. So the span of a single vector is nothing more than just the set of all scalar multiples of that vector. So we know that this is a linearly independent set. The solution set to this system consists of the span of this vector, that is to say all scalar multiples of this vector. All right. So you can see that S, the solution set, is just the span of this vector. And we know that this set containing this one non-zero vector is linearly independent. See, another nice thing about a set of containing a single non-zero vector is such a set is always a linearly independent set. So since the set containing the vector negative 5, 1, 3 is linearly independent, that's this set, negative 5, 1, 3, is a basis for the solution set to the system, which we're calling S, right? Okay, this brings in another question up. All right, so you might see this. Just a few asides then. If a set contains a single vector, big V represents a vector space, and here is a set that contains little v, a vector that's in big V. So this set is a subset of the vector space big V. Then this set containing the vector little v is linearly independent so long as the vector is not the zero vector. The proof of that Why do you show that a set of any vectors is linearly independent? You set up a linear combination of those vectors and set it equal to the zero vector, and then show that all the scalar coefficients have to equal zero, right? So in other words, we do scalar multiple of the vector v and set that equal to the zero vector, and show that the c has to be zero. Well, okay, so we're supposing this. I don't know if I can fit this in here now. Suppose this. We had actually already shown early in chapter 3. It's established in the notes at the very least. I'm pretty sure it's established somewhere in the textbook. That if a scalar times a vector is equal to the zero vector, then one of two things must be true. Either the scalar is the number 0 or the vector is the zero vector. So either the number c is 0 or the vector v is the zero vector. But we're assuming that v is not the zero vector. Therefore, we must have c as 0. Pretty cheap. Not much going on there, right? It's really a proof that doesn't really involve too much. So if we set c times v equal to the zero vector, the only possible solution, if we're assuming that v is not the zero vector, is to have the c be 0. By definition, that means that the set containing the vector v is a linearly independent set. So another therefore is in order. The set containing v is linearly independent. Here's another thing to prove. If, how shall we put this? If S subset of V contains the zero vector, okay, if the set S, which is a subset of the vector space V here, contains the zero vector, then S is a linearly independent set. We're assuming that S contains a finite number of vectors. At least for the sake of argument, we can assume that. So we're taking S to be some set of vectors in V. So let's say it's got vectors V1 to Vn, say, and then also the zero vector is in there. Now then, oh dear, I got this wrong. S would be a linearly dependent set is what I'm trying to show here. Not linearly independent. So any set of vectors that happens to contain the zero vector will be a linearly dependent set of vectors, so not linearly independent. Okay, that's what we want to show. What you do is the usual thing. You set up a linear combination of the vectors in S, set that linear combination equal to the zero vector. C1 V1 plus dot 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 Cn Vn. Of course, there's one more vector in there after Vn, which is 0. We'll have to have the coefficient of 0 be like, say, Cn plus 1. How about that? Times 0 is equal to the 0 vector. So to show that the vectors in this set S are linearly dependent, it's enough to just show that not all of these numbers, C1 through Cn plus 1, have to be 0. Well, in fact, that's possible. They don't all have to be 0. One solution here is to have C1 equal 0 all the way up to Cn equals 0. So C1 through Cn, they'll all equal 0. And as for Cn plus 1 there, in front of the 0 vector, well, so let that equal 1. Zero V1 plus 0 V, and so we have 0 V1 plus 0 Vn plus 1 times the 0 vector. And that, we already know, again, early on, look in the notes in section 3.1, one of the first few pages, when vector spaces were first introduced. There I know it was shown that the scalar 0 times any vector gives you the 0 vector. This continues all the way over to here. 0 times Vn gives you the 0 vector. It was also proven in 3.1 that any scalar times the 0 vector is likewise the 0 vector. So we have 0 vector plus 0 vector plus 0 vector. Okay, so we can see that all of this just becomes the 0 vector. So we get this, right? We end up with the left-hand side is equal to, in fact, the 0 vector, but we don't have to have all the coefficients C1 through Cn plus 1 equal to 0 to do it. The first in will have be 0, and then the last one, that can be 1. I could have let it be 2, or any other non-zero scalar would do. So this, yeah, here, I'll say equals this equals the 0 vector. So that's the thing. Therefore, the vectors S here, the set S, is linearly dependent. So these are just some things here that are good to know. So if you have a set containing a single vector and that vector is not the 0 vector, that's a linearly independent set. So here, as I say, this set here is linearly independent, and since it spans the space in question, the solution set to this system, namely, then that set is a basis for S. Okay? A basis for any vector space is a spanning set for that space that is linearly independent. All right, let's rock and roll with some more fun stuff. Linear independence of functions. let V be a vector space consisting of functions f that map from some, say, interval of real numbers, for instance, I, to the reals. So we have seen that a vector space can consist of all sorts of different things. R3 is a vector space consisting of ordered triples of real numbers. You can have a vector space consisting of 2 by 2 matrices, or m by n matrices. You can have vector spaces consisting of polynomials of degree at most 5 or something. Or you can have a vector space consisting of, say, functions all defined on some interval I. Okay, we've seen this in chapter, well, a few sections back. So what does it mean for you to have linearly independent vectors in this context, for sort of a vector space like this? Okay, well, so let F1 through Fn be a subset of V. By definition, this set, F1 to Fn, is linearly independent. If the sum k equal 1 to n of ck, fk equals 0, implies necessarily that all the ck's are 0. Ck is 0 for k from 1 to n. Now I'm just using the summation notation here, but you could write this out in the usual expanded way: C1 times F1 plus dot 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 Cn times Fn, and that's equal to 0. It should be borne in mind this is the this 0 here represents the 0 function on the interval I. Let's see here. That is to say, it's the function that takes each number in the interval I and returns the number 0. i.e., the 0 function evaluated at x is equal to the number 0 for each x element of the interval I. So you're summing up a bunch of functions over here, and when you do that, the result will have to be a function again. So the 0, bear in mind again, is representing the 0 function, not the number 0. So you just have to ask how this works. But this is just from the definition of linear independence of vectors in any given vector space in general. There's really nothing too new here, really. So what we're saying here is that this function on the left-hand side of the equation, the sum of ck fk as k goes from 1 to n, this function is precisely the 0 function on I. Here's a little example. let f1. Okay, so first of all, yeah, let's see. Let v be the vector space of real valued functions on R. So in other words, v is equal to the set of functions that map from the reals to the reals. Set of all those kinds of functions. So we could have like f1 of x be, I don't know, let's say x e to the 2x, and f2 of x will have be e to the 2x. See, these are definitely functions that are defined on the entire set of real numbers, right? And they're real valued functions. They map the reals to the reals. So I would say, to complete this sentence, so this function and this function are elements, i.e. Vectors in V as defined here. Suppose C1 F1 plus C2 F2 is equal to 0. Now, just keep in mind that in this context, we're talking about a vector space consisting of functions defined on R, the real numbers. So all functions in this vector space V are functions that have domain all reals. When you write this, you're saying that C1 F1 plus C2 F2 evaluated at x is equal to the 0 function evaluated at x for all x element of the reals. Now, I know this looks perhaps a little strange, but I mean, whenever you're dealing with functions, this is the stuff that's going on. We already have defined what we mean when we take the sum of two functions, right? We take f1 and multiply it by c1, and that makes a function. And f2, likewise, defined by the scalar c2, gives you another kind of function. I mean, we know that this, by definition, is when you put x into this function, you're putting x into this function, c1f1, and this function, c2f2, right? And we also know that 0 of x just equals the number 0. This is the number 0. I'll put a little pound sign there just to make it clear. This is the real number 0. This here is c1 times f1 of x, right? The function c1 f1 takes in x, and what you do is you put x into the f1 and get a number, and you multiply that number by c1, which is a scalar. Same here. Right? And that's equal to the number 0. And we're doing this for all x element of the reals. Okay, is it possible for this to hold, for this to equal the number 0, for all x real, okay, without resorting to having C1 and C2 just both equal the number 0? Is there a way to do this? I mean, f1 of x is x e to the 2x, right? f2 of x is e to the 2x. And that's equal to the number 0. I'll probably quit writing that because I think it's getting obvious now. So this is for all x element of the reals. Well, let's play with this. So let x equal 0. For instance, this has to hold when x is equal to 0, right? We get C1 times 0 e to the 2 times 0, right, plus C2 e to the 2 times 0 is equal to the number 0. Well, C1 times 0 times e to the 2 times 0 power, well, this is just 0, right? Yeah. And then here, this is e to the 0 power, that's just equal to 1. And this equals 0. So 0 plus C2 is 0. Oh, so we have here that C2 has to be 0. All right. Well, let's take this. So that kind of blows that away, right? Now we have C1 x e to the 2x is equal to 0 for all x element of the reals. Ooh. Now let x equal 1. We get C1 times 1 times e to the power of 2 equals 0, right? Well, C1 times e squared equal to 0 can only happen if C1 is 0. So C1 and C2 both have to be 0. So this shows that, in fact, F1 and F2 are linearly independent. Just squeeze down here in the corner. Therefore, F1 and F2 is a linearly independent set. Okay, that's the first example. Now we can do another thing here. Let's look at some other functions. How about this? F of x is x squared. G of x is 6x squared minus 1. H of x, this is another example, I suppose I should bill it as such. H of x is 2x squared plus 3. We could just continue to suppose that these are functions in the vector space V consisting of all real-valued functions with domain all reals, like in the previous example. That's fine, whatever you like. But they're all polynomials, you can see this. The question is, are these linearly independent? or not? Okay, well, we do the usual gimmick. Suppose, let's use A and B and C instead of C1, C2, C3. How about? So AF plus BG plus CH, set that equal to 0. If these functions f, g, and h are linearly independent, then it must be that a and b and c have to be 0. In other words, if the only solution to this is to have the scalars a and b and c all equal to the number 0, then the functions f, g, and h are linearly independent. I guess I should mention here, we assume that f, g, and h map from the reals to the reals. Why do I even say that? Well, I mean, we could assume that f, g, and h map only from the interval from 0 to 1 to the reals or something like that, right? But we'll have their domains be in fact all reals, like I said about a few minutes ago. If you wanted to have it be a different interval instead of all reals, you could, but this will work for our purposes. So what we have here is that a f of x plus b g of x plus c h of x is equal to the number 0 for all x element of R. It's ax squared plus b times 6x squared minus 1 plus c times 2x squared plus 3 is equal to 0. What do you do? This has to again be for all x element of the reals. So what happens if we have x be 0? If you let x be 0, this is gone. You get a times 0, that's gone, plus b times 0 minus 1, so you get negative b, plus c times 0 plus 3, so that's 3c is equal to 0. In other words, b should be b has to be 3c. That's no choice. Well, ax squared plus 3c times 6x squared minus 1 plus c times 2x squared plus 3 is equal to 0. Here's what I suggest doing. Just combine the like terms. You have an a plus 18c plus 2c. Well, in fact, you can put these together, right? There's 2c x squared and 18c x squared here. And then, what else have we got? We have negative 3c plus 3c. Well, that's interesting, isn't it? Negative 3c plus 3c. Well, that's gone. So we have a plus 20c times x squared is equal to 0. Now that certainly could be satisfied if you let a and c both be 0, but there's definitely a way to do it without having them both be 0, right? One solution, let c equal 1 and a equal negative 20, right? Then you have negative 20 plus 20 is 0 times x squared will give you flat 0 all the time. And this also would have to mean with c equal to 1, b would be 3. So if we let c be 1, a be negative 20, and b be 3, we satisfy this for all x element of the reals. And therefore we satisfy this. You can check this out. A is negative 20 times f plus b's 3 times g plus c is 1 times h is we don't know it's equal to 0. We're going to check that. Okay, so that's equal to negative 20 is at times the function f, that's x squared. I guess, you know, really, oh boy. Let me write this again. We're putting x into this guy, any real number x. Now, negative 20 times f of x, which is x squared, plus 3 times g of x, which is 6x squared minus 1, plus h of x, which is 2x squared plus 3. And you can see you get negative 20x squared plus 18x squared minus 3 plus 2x squared plus 3. And they cancel, that cancels, and that cancels with that guy and that guy. And you get 0. So there you have it. The set FGH is linearly dependent, not independent. Okay, so there we have another example involving linear independence of functions.